Okay, we continue. Not that much left with multigrid. Should be finished with this one today. So V cycle and a mu cycle, that's the one that takes a little bit up and down and up and down. We don't have to go through this. How you can program it recursively, rather messy. And then also this full multigrid method. So you start on the coarsest mesh and then nest your way up to the finest to start to find a better initial solution on the fine mesh. Yes, that's an option. So yeah, we don't have to go through all this. Required storage, as we spoke about, you need two entire vectors on each level. But depending on here how many dimensions you are having, 1, 2, or 3 dimensional problem, you see the additional storage to the fine mesh solution will be quite small. So of course, 1D case, you will have there 1 plus 1/2 plus 1/4 and so on. But I mean, a one-dimensional problem, that's not realistic. We are talking, of course, always 2 or even 3D problems. And in 3 dimension, on the second grid level, you only need 1/8 of the entire memory storage from the fine mesh. So it's very economic when it comes to required memory. Very economic. A little bit about these programs that has been used here. We won't go through it in detail, of course. A couple of examples, and then sort of the way to think when you construct a problem. Here is sort of a reversed engineering. You start with one single cell, and then you just choose how many levels you want to use, and then you end up, say, after 10 mesh levels, you end up with quite a number of unknowns in the end. But also in 2D, of course, even worse. So you have to be careful if you want to define the problem like this, starting on the coarse mesh and then say, I want 8 mesh levels. Then you blow the memory on the fine mesh fairly easy. How big is this number? 17 million unknowns, thank you. You need a big computer already. When you are talking about efficiency, you need to define for the different mesh systems what is the number of operations needed to perform or to do the calculations. And I mean, one iteration on the fine mesh can be can take some time, but one iteration on a coarse mesh might go very rapidly. So to talk to each other there, the number of operators involved, depending on the mesh, we sort of translate everything into what's called a work unit. And the definition for a work unit, that is one iteration on the finest mesh. So that means in a one-dimensional problem, the coarse mesh has only half as many points. Then one iteration will be 1/2 work unit, and so on. So then it's easier to calculate, okay, how many operations in total is then required to do, say, a V cycle or whatever. So work unit, that's the amount of operations needed to perform a V cycle, whatever. Yeah, the error calculations here quite tedious, and as actually we really don't need them. This is something if you can study if you're interested. Cost of a V cycle, and so on and so forth. So we instead jump to these examples that we have here, and we have 2 of them. The first one-dimensional problem. That's the Poisson equation we are searching for, finding the steady state solution for a flow between two parallel plates, the parabola, double derivative equal to -1. And you have that one in the appendix as well. So here, the plane Poisson flow between two parallel plates. Here you have the reduced Navier-Stokes with dimensions. Then it's possible to redefine the equation and rewrite it in a dimensionless form to have it like this, which then will be our model equation here. We know the analytical solution, so not a problem there. Analytical solution, then infinite Fourier series here. The choices, the setup parameters you can see for yourself. And here is an attempt to describe the use of the memory. And this is sort of the headache when you're doing programming in general using Multigrid. And here they put all the unknown into one long big array. And then you need pointers inside that array to say, these are the unknown on this and this grid level. So it's a lot of bookkeeping here. You might want to program it differently, creating one matrix or one vector for each of the different mesh levels. Your choice. But here it has been done like this. So the first program is called vduct number 1. That's pure V cycles. And then you have something called an S-duct. That is, you start with the coarse mesh and then work your way up on the fine mesh first, sort of a full multigrid. Name of the different routines. Yeah, you can look at this one if you are interested. So there you have the two different codes. vduct, only V cycles. S-duct, start first initially on the coarse mesh before you entering the ordinary V cycles. And the printout should be given here. Just for comparison, here it's solved the same problem using an SOR, but now with an optimum omega, 1.85 for this problem. And the work units here, they are just ordinary iterations using standard SOR just to find a solution. And you needed here 50 iterations equal 50 work units to get the anode down to this level. Then we have something to compare with when we do the same now with Multigrid. So SOR should be fairly efficient. Now let's see how Multigrid compares. Now this one is the ordinary V cycle. You start with the finest mesh. The anode printout, that can only be calculated then on the fine mesh, of course, because the anode on the subgrid systems, they will be from the residual equation. It makes no sense. So it's only on the fine mesh that we actually can get any sense out of it. Here it's only one iteration, one relaxation on the way down, from the fine mesh to the coarser and coarser mesh, only one iteration at a time. Then you see the work units here has been accumulated. On the fine mesh, one iteration. On the second mesh, also one iteration. Okay, then we are up in 1.5 for work units and so on. On the way up again, you do two iterations. So there you see 1, 1, 2, 2, 3, 3, and so on for the different grid levels. So after one single V cycle, we have reduced the anode a factor of 10. And we have done that in only close to 6 iterations on the finest mesh. So yes, it's fairly efficient. And here another V-cycle. So then you see the anode is getting really small already after 11 iterations. So yes, it's fairly efficient. Now this is a one-dimensional problem, and frankly we don't have that many unknowns here, so you don't really see the full power of the multigrid compared to the example we had here with SOR, 50 iterations, but still definitely more efficient than standard SOR, even for such a small case as this. Here is the printout from the other version, the S-duct one. There you started on the coarsest mesh and then nested your way up to the finest to get a better initial solution. You see, and that's actually here a very good idea. You have a very small anode already. And then ordinary V-cycles, and we have 2 of those. So in the end, here you see an anode 7 to the power of minus 10, and then after only 15.5 work units, meaning 15.5 iterations compared to the SOR up here. But he needed 50 to get to the same anode level, so definitely more efficient. And the difference will be even stronger here in 2 dimension. Model problem number 2 is sort of the same problem, but then 2D. So now you have laminar flow through a square duct, and also here you have an analytical solution, so you have something to compare with. The analytical solution here is not so easy to calculate, but I mean here you have it, so you can use it, and it's quite efficient. It's a nice test case anyway, so nice to know these analytical solutions. Anyhow, the printout from this one, well, the same here. We use an SOR. Here, optimum omega 1.94. You see, we needed 80 work units, 80 iterations to get the anode on this level. And this one we don't need. Here's the printout from the V-duct code, starting on the fine mesh, telescoping your way down to the coarsest mesh, and then go up again, 2 iterations on each level on the way up. Then here actually only 4 iterations of work done, and the anode has been reduced quite substantially. Then another V-cycle, and even a third V-cycle. The anode is getting very small with only 12 iterations. 10 to the power of minus 3. The SOR needed 80 iterations to do the same job. So yes, it's decent. And if you go to 3D, it will just be better and better and better. And also if you increase the number of points, remember multigrid will be linear if you increase the number of unknowns. SOR, he will go exponentially, more and more work he needs to do it to find a solution, so he will be bad. Here a little bit more heavy math if you want to find these different optimum values, convergence rates, what should you do on one level. Is it smart to stay there, do another iteration? Is it smart to jump to a coarser or finer mesh from here? A lot of theory behind this, so I would say forget it. But if you're interested, you can read it yourself there. Now, stopping criteria. This is important in practice when you're using multigrid. Sometimes, somehow you have to tell the algorithm, now you should terminate. The anode is smaller than something, stop. And then how should you choose the anode level there? That can be difficult, depending on your original problem. Like you only have an algebraic equation system, something like this. And yes, you can find a residual, but as we already discussed, using the residual as an Arrow indicator, very dangerous, very, very dangerous. What we would have liked to have is, of course, the Arrow given us the difference between the perfect solution from this and our numerical, but we don't have the perfect solution, so in general. So how to find a stopping criteria? That can be a pain. So in most codes, you have to rely on the residual, and that can be very, very, very dangerous. You never know what these numbers actually mean, since, as I say, you can multiply the equation with whatever you want and have a totally different value for this residual. So typically what you do, you look at the reduction of the residuals depending on how many iterations or V cycles or whatever. And when he has been reduced by, say, a factor of 3 or 4 decades, meaning a factor of 1,000 or a factor of 10,000, then you say, I'm satisfied. But then you really don't know if the error is small. So what would have been nice here would be to have an indicator with a little bit physics in it. But that depends on your problem. If you can recall the Sola algorithm, projection method, what did we do? Well, we constructed a Poisson equation for the pressure difference between the new and the old pressure. That was equal to the something, I don't remember, and then we had the divergence of the tentative velocity field, something like that. And during this, well, we solved this one with an SOR, and during the process we had to calculate or re-update the velocity field, and then finding the new value for this divergence, which then is the right-hand side of the equation system. And there you have a beautiful stopping criteria. You evaluate the divergence all the time from the freshly updated velocity field. And the divergence, that's a quantity with physical meaning. If the divergence is so and so small, then you can tell how good is my solution. So here you definitely have the possibility to sort of decide your arrow level with a physical meaning instead of just using the residual. Also, as I mentioned initially, solving this equation perfectly down to machine accuracy, you can do it, but it's a waste of time because you have an arrow in your equation system already, since from the real partial differential equation you have to discretize it. You'll have an arrow of order delta x square or whatever you have decided what kind of order you have in your scheme. So you're going to have an arrow anyway. So pushing him all the way down to machine accuracy, waste of time, waste of time. So you should stop when you have some physical interpretation that now you are satisfied with. That would be the best. And in Sola, yes, that's possible. But typically here, you just look at the residual norm. Also, I remember one version of Fluent, an old one. They did it very dangerously. They took the first iteration, or the first time step, calculated a residual 0. And then they used this one as a scale for the next 10 millions of iterations that you were going to need. So the residual that he actually printed out on the screen was a non-dimensionalized with the first residual. But these stupid amateurs programming Fluent in those days didn't think the thought that what do you normally start with for a case? You start with everything equal to 0. Then he was 0, and then you divide by 0. The residual was 1 million or bigger and refused to be smaller. You couldn't get a solution at all. Very bad idea. Amateurs. I don't think they do it anymore. Yeah, I won't go through any of this. The output should be rather boring. We even got the Pascal programs, and that's one we actually got from Archie Brandt. So then that was sort of fun, but I guess none of you have programmed in Pascal, so just forget it. A final little note. Using multigrid in a sort of different way of thinking. Now we haven't done much turbulence yet, but we are going to. And the best turbulence description that we have is without any model. You solve the Navier-Stokes directly, but that means you need a tremendous amount of cells. Your cell has to be down to the smallest turbulent vortex in the flow, and this is expensive. So using a direct numerical simulation, you need a very big supercomputer for even moderate Reynolds numbers. So as a test case here, the simple Poisson flow between two parallel plates, Reynolds number is 3000, is just turbulent. You needed some 2 million grid points just to describe what's going on here. Furthermore, you also need time steps, delta t, down to the turbulent smallest time scale. And that delta t is very, very small indeed. So for this very simple problem, you're going to need many, many hours on a supercomputer. Nowadays, it's not that heavy actually. You could do this on a laptop, should be possible, but it's going to take a couple of days of CPU. So this is the problem now with a direct numerical simulation. He doesn't model anything. And, well, just to show you, for this problem, the flow between two parallel plates, solution is then a turbulent velocity profile, something like that, on average. But as a snapshot, instant velocity profile, he doesn't look like this at all. You will always have the no slip condition on the walls, but an instant velocity profile could look something like this. So of course you have no need for all that detailed information. You want an average solution. So how to create an average? Well, you had to do it over and over and over again, simulate for a very long time, and create a good statistics. That's the problem with DNS. You have to do it for a very, very long time. Furthermore, to get things started, what I did with this simulation here, I started just with everything equal to 0 and then put on a driving force and let the computer start calculating. That turned out to be a very bad idea because I got the laminar solution. Although the Reynolds number is 3000, so he should be unstable. But remember, a laminar solution is still a solution, so he was happy with that. So then I did it again, and then I used a random generator to produce a whole lot of noise for all the velocities throughout the domain, and then started over again. And then I had to monitor something to sort of decide when is the flow fully developed, when do I have steady turbulent flow. And what I did, I looked at the turbulent, well actually the total kinetic energy. But this one was now averaged for the entire volume. I had to do it in 3D. The turbulence is by nature three-dimensional, so you have no choice. Full 3D. So I calculated all the kinetic energy, and then I plotted that one versus time. What happened was, since I used a random generator initially, just produced a lot of noise, which was unphysical, he was sky high. But then after a very short time, a couple of time steps, he was reduced to almost 0. And that's due only to the continuity equation, damping out all these random velocities and pressure, which was very unphysical. And here I started to get worried, because now he was closing down to 0 for the turbulent kinetic energy. And if he is 0, then it's laminar. Now in those days, this was in the 80s, I run this one on the Cray 2 computer in Lausanne in Switzerland, and one CPU hour costed 20,000 crowns. And I had to run for several thousand CPU hours. I spent 9 months on that simulation. So you can imagine this was expensive. So here, sort of the taxameter was running, and I saw that my solution, he's going to die. But finally he started to build up with the turbulent kinetic energy. Then I was worried, will he explode? But finally, after some time, he leveled off. And from here on, I could now say, now I have a steady situation. It's still full turbulent, violently behavior, but from here on I could start calculating data. I could start making statistics. And to get there, I think I spent 1,000 CPU hours or something before I could even begin obtaining solutions. But now I could have used some multigrid idea, because what I really are interested in is a whole bunch of different solutions of the Navier-Stokes. I mean, this is the way you should look upon a direct numerical simulation. It's not possible to say we solve everything. So you take, in a wind tunnel, you can drop a feather at the inlet, let the feather follow the turbulent flow, and then determine exactly where that feather is going to end up on the other end. No way. You can't do it. You need millions of time steps, and you're going to accumulate errors anyway. So the way you should think of a DNS, produce a whole bunch of different solutions of the Navier-Stokes, and then you make an average. So what I needed was a good bunch of solutions. But one solution should be sort of independent of the next one. So if I were to pick solutions from every time step, that would be a waste of time, because during one single time step, you didn't have much change. So the new velocity field is going to be very similar to the one from the previous time step. So then typically I waited 500 time steps or so before I took another sample. And so you continue for every 100 time step or something. Then you have another solution which is uncorrelated with the previous ones. That made more sense. But you need many of these. And now solving the Navier-Stokes on a fine mesh using DNS is very expensive to go from here to here. How could you do that faster? There you can use the idea of multigrid. So on the fine mesh, let's see here. The fine mesh, that was 128 cubed cells. You do a sample, and then you sort of transfer your problem onto a coarser mesh, which then has only 1/8 of the number of cells, 64 cubed. That's a factor of 8 in reduction. Also, now my mesh was so crude I couldn't really call it a DNS anymore. I had to switch on a turbulence model, a large eddy model, to be able to do it. But yes, it was possible. And then I could travel from here, and now on a coarse mesh down here much faster. And then when I had achieved enough time here, I wanted a new fine level solution. Then I had to jump up to the fine mesh and simulate some time steps here so that I had the new turbulent structured reorganized correctly, and then do another sample. Then I could reduce the cost quite a lot. Actually a total gain of factor of 16. So absolutely possible, yes. But it was sort of tricky. And now you are not talking real multigrid. Fair enough, I had 2 different grid levels, the fine and the coarse, but nothing more. But then I didn't take my Poisson equation or something like that. I took the full entire Navier-Stokes, everything. and just solved it on a coarser mesh system. So that's actually not the way we think in terms of multigrid. Finally, I just want, well, reference of course. Here the book by Briggs, definitely recommendable, easy reading. The other one here can be very heavy, and some of them I will not recommend you to even open. So Wesseling, Hackbusch, these guys, they are very clever when it comes to numerical theory, but wow, they are heavy to read. Try to open one once. I will never do it. Yeah, the final thing, that was the problem of actually doing this with never mind that, we don't need it. When you have nasty geometry, so if you have this nice rectangular area, no problem. Of course you can divide these into finer and finer meshes, and your coarsest mesh can be just one single big cell, beautifully, not a problem. But you have here a flow around a house, something like this. Okay, simulate this one. That's not so easy. The coarsest mesh must still cover the geometry, so this will not be easy. Typically what people do here, they split it up into blocks, maybe something like this, and use separate multigrid algorithms for each block. Tricky, then the blocks has to talk to each other, but I mean you have to do something here, because the coarsest mesh here, if you have complex geometry, it can't really be covered. And also you have the problem when you are on the coarse mesh systems, you also need boundary conditions on every level. Remember, the equation system is elliptic, so you need boundary conditions all around, also on coarse meshes. And to program it, that was tough, very tough actually, so I won't recommend it, writing your own multigrid code. These model codes that I found here, they are fairly easy, you can see for yourself, but doing this in a general way, it's hard, very hard indeed. So this makes multigrid in general hard to program. When you search for multigrid codes or multigrid subroutines, you can find it, but you will not normally find it in the way it has been described here. You will find it in a mathematical way, and then we call it algebraic multigrid, meaning that you take your original problem, you have to formulate this one somehow on the fine mesh system, and you give this problem now to a mathematician, and he will then solve it or write the algorithms for you without thinking anything about the physics, without trying to use some benefit of the geometry in the problem, nothing like that. It's pure math. Sort of how to translate this problem, including the boundary conditions, into a structure that can be solved mathematically. That's an algebraic multigrid for you. It's not so efficient as what it could have been if you had programmed it sort of yourself, where you can then program your own subroutines, your own boundary conditions on every grid level, but it's a tough job. So using an algebraic multigrid method, that is typically what you are going to do. That's what you are going to find. And to be honest, they are not so stupid. The programming inside them will be very heavy to understand, so I won't recommend it. Trying to write your own, and why should you? You find plenty of them around. but it's heavy. It's heavy, absolutely. What's nice about them, if we shall summarize, they are very efficient. Even the algebraic multigrid there, is close to order n operation with order n unknown. Very efficient. They don't require much memory. You need, say, maybe twice as much in memory space as you already have from your unknowns. So very economic when it comes to memory. It's not so fun to do the programming here with a huge parallel computers. That's not funny. How can you sort of divide up the problem so that one CPU can take care of this part of the problem and another CPU take care of this part? They talk very much together. Using multi-block, saying, okay, we take one region here and that one CPU solve one multigrid for this area, another CPU for the other areas, and then of course you need boundary talk. That's possible, but a full and ordinary general multigrid code, not so easy to make a parallel version of it. But yes, of course possible. You find it in libraries, computer libraries around the world, but tricky. So that's sort of one negative way, negative point with multigrid. Okay, then I think we have said enough about multigrid. The other, where is it? Here is it. The different appendixes shows you actually here the Fortran 77 source codes. So not so fun to read maybe, but you have them. And you even have the Pascal codes, I think, here somewhere. Yeah, you can have a look for yourself if you are interested. Yeah, Pascal programming. Pascal sort of before we had C. Integrate transfer, we'll talk about that. So more numerical theory here, which actually then we don't need. Yeah. Finally, if you have problems initially now with using the residual equation. Remember the demand, your equation system had to be linear in order to produce a residual equation. Now, if suppose you have a nonlinear system, then you can forget all about the residual equation. Then you have to use the original equation representation on every level. You can do it, but it's not so efficient anymore. So it's described a little bit here. Now it's quite rare actually to have a nonlinear coefficient matrix A, so you really don't need to worry too much about it. Yeah, I think we stop here. That should be everything, I think. So next time will then be Wednesday. We talk about Krylov methods, conjugate gradient. And then done with that, we are going to look into finite volume and unstructured mesh systems. Any questions from you? Then we stop here.